Hello learners, welcome to Sure Question Academy. Please watch the videos, like and subscribe to the channel.
Hello everyone and welcome back to our physics class. Today, we are going to tackle a brilliant question that tests our understanding of solenoids and electromagnetism. Make sure you have your notebooks ready and let's decode this step by step together. Let's start by looking at part A of the question. Imagine you have a solenoid, which is just a coil of wire named AB. Now, a magnetic needle is placed right near end B of this solenoid. Look closely at the diagram on the screen to visualize the setup. Here comes our first sub-question. When we turn the switch on, current starts flowing. The question asks, which pole of the magnetic needle will be attracted to end B of the solenoid? Take a guess. If you apply the clock rule, you will realize the current at end B flows anticlockwise, making it a north pole. So naturally, the south pole of the magnetic needle gets attracted to it. Let's reveal the answer. South pole. Now for question B, explain how you arrived at this answer. In board exams, just writing south pole isn't enough. The examiner wants to see your logical reasoning. Let's break it down. Here is how you should explain it in the exam. When electric current flows through the solenoid, and B behaves exactly like the north pole of a magnet. From basic magnetism, we know the universal rule, unlike poles attract each other. Therefore, the south pole of our tiny magnetic needle is strongly pulled towards the north pole at end B. Moving on to question C, suggest 2 ways to increase the magnetic strength of a solenoid carrying an electric current. This is a classic question, and it has a lot of real-world applications in making powerful electromagnets. There are a few clever ways to boost that magnetic field. Let's list the top 2 methods that you should definitely write down. Number 1. Increase the number of turns in the solenoid coil. Think of it like adding more tiny magnets together. The more loops of wire you have, the stronger the combined magnetic field becomes. Number 2. Increase the intensity of the electric current. More current means more flowing charge, which directly pumps up the magnetic strength. A bonus tip, inserting a soft iron core inside the coil is also an excellent method. Awesome job on part A. Now, let's examine the alternative question. Part B says, a current-carrying circular loop is placed near the end B of a solenoid AB. To push current through the solenoid, a battery or cell needs to be connected between points P and Q. Take a look at the second diagram to see this arrangement. Question A. Which terminal of a cell should be connected to point P so that the circular conductor loop is repelled from end B? Remember, repulsion happens when similar poles face each other. For the loop to be repelled, end B must form the same pole as the loop facing it. For this to happen, the current must enter such that the field opposes. Therefore, the negative terminal of the cell must be connected to point P. Next up, question B. When the magnetic flux produced by the main solenoid is increased, what change occurs to the magnetic flux produced by the single circular loop itself? This is a bit of a trick question. The flux of the single loop itself doesn't just magically increase. So, the correct answer is no change. Let's tackle question C. If the positive terminal of the cell is connected to point P and the negative terminal to point Q, at which end of the solenoid will the north pole be formed? If you trace the current from positive P to negative Q and use your right-hand grip rule, your thumb will point towards the right. This means the north pole will be formed precisely at end B. Finally, we have question D. How does the magnetic field produced around a current-carrying solenoid differ from the magnetic field around a permanent bar magnet? They might look similar, but they behave very differently. Here are the two fundamental differences you need to highlight for full marks. Difference 1. The magnetic strength of a solenoid can be easily increased or decreased by simply adjusting the electric current. But for a bar magnet, the magnetic strength is completely fixed and permanent. Difference 2. This is the coolest part. The poles of a solenoid can be instantly reversed just by changing the direction of the battery current. You definitely cannot flip the north and south poles of a solid bar magnet. And there we have it. We've beautifully solved the entire question, understanding the why behind every single step. Thank you so much for joining this session. Keep practicing, stay curious, and happy learning.